So this is a very exploratory talk. I kind of committed myself to give this talk in order to go through more carefully through ideas I've been thinking about for a while. There are some technical nuggets in the talk, and there are work with Konstantin and Jennifer Welsh and Nitai, my master's student who's at the back. But all the musings and all mistakes are mine. And everything is correct is theirs, the rest is mine. Okay, so abstraction is a great idea. Okay, and it's been extremely successful for concurrent objects. We've seen several instances today. And basically what we have is we have an abstraction, a specification, and then we have a concrete implementation. And basically, we show that the concrete implementation is a refinement of the abstract specification, the abstract object, and then we can basically replace the abstract object with the implementation, and everything is great. It's not so great, but still it's been very effective for us, and a prime example that we've seen several times today was linearizability. But this hasn't been so successful for distributed protocols. Okay, where the communication is done usually through shared memory, and protocols are activated in a way that overlap each other, and there are no like clean boundaries between the modules that we are using. Okay, and I want to argue that part of the problem is inadequate specification tools. So the problem is not refinement, not just the refinement methods, not just the way we write implementations, but the way we specify what we want from protocols is inadequate. Okay?
Yes. Can you say again what is the difference between the protocol and the concurrent data structure?
Concurrent data, so think about linearizability versus, I'll do several examples actually. Maybe let's skip it. Okay. In a minute I'll show you what I mean, an instance of protocol. Okay, so, and I want to suggest a path that might help to partially deal with this inadequacy, okay? So here's an example, okay, as a protocol several people here worked on. Is called Crusader agreement. It's actually introduced in Danny Dolov's paper on Byzantine agreement. And so this is the definition. He has agreement A, which is Crusader agreement, and then agreement B, which is actually real Byzantine general's problem. And I don't expect you to read this if you haven't read this before. Instead, I want to give you a clipping from a paper by Abraham Ben David and Yan Damori from POTSI 22, sorry. And actually, let me use a specification Jennifer and I introduced in this afterwards. So basically, we have, instead of the usual consensus problem with the 0 and 1 outputs, we have consensus, same, 0 and 1 inputs, but we are allowed to decide on 3 possible values, 0, bottom, and 1, with the condition that if all of us, all the correct processes start with 0, we decide 0, all of us start with 1, we decide 1, but when there's a mixture of inputs for correct processes, we are allowed to decide on different nodes here. But one of them must be bottom. So basically we can have bottom and 1 or bottom and 0 in the situation when not all correct processes have the same value. And Crusader agreement in various forms. Next slide is an oversimplification. But Crusader agreement has been useful in several protocols, in particular for randomized consensus, for example. And what happens there is that you run Crusader agreement kind of to see if we already agreed. And if we already agreed, then we'll agree on this value, V. And if there's some disagreement, some of us might go out with some value, the same value for all of us, and some of us will go out with bottom. And if you get bottom from Crusader agreement, you'll go into a common coin protocol, you flip a coin, okay? And if you're lucky, the coin will come out to be the same value V that came out from Crusader agreement. So with probability half or close to half or at least non-zero, we'll agree between the common coin and the Crusader agreement, and we have some chance of terminating. because what we'll do next is we'll feed these results into crusader agreement again. So if we got agreement, we'll decide on that thing, and if not, we'll flip a coin again, and again, we have some luck, and so on and so forth. Okay, so that's an oversimplification, but still a fairly reasonable way to think about several of the randomized consensus algorithms.
Do you know that you got agreement?
Say it again.
Do you know?
So there are questions, when do you know to terminate, blah, blah, blah. Let's leave them alone. Thing is that it's not so correct, especially if your adversary is adaptive. So if you have an adaptive adversary, what happens, this is where the difference between a protocol and a shared memory object comes out. So what happens is, you see different, it's pictured here as if we go nicely between the modules, but actually we don't, okay? So basically there might be some process that leaves the crusader agreement with a bottom, meaning that it's going to flip the coin, okay? So it flips the coin, the adversary sees what value the coin landed on, and then, since some other processes might still be in the crusader agreement, it could go back into the crusader agreement and bias the processes to decide to have their non-bottom value be the opposite of the coin. Okay? And with luck or misluck, you could have a situation that the adversary can always, with probability 1, or can always ensure that any of these iterations never terminate. And that's even when the common coin is perfect and nice and so on and so forth. And this has been actually hidden in several algorithms. In fact, this paper that won the best paper in this 2014 and actually had this mistake, and it had to be corrected. So there are ways to correct for that. Okay? So as I said, I'm oversimplifying. Okay, and this, so to explain what's happening and how to mitigate that, let me actually start to talk about the crusader agreement specification. And what I want to tell you is that, or to argue is that we want to think of the non-bottom value, this value that needs to agree with the coin, essentially, in this the scheme that I've shown you. We want to make it a first-class citizen of our specification. Okay? So, again, I'm lifting or borrowing the picture I had for concurrent objects, and I want to have this for the crusader agreement, so I have an indicate saying I'm process I, and my input is xi, and then I get a response, process I, saying, okay, your output is vi, which could be either bottom or 0 or 1. Okay? Okay, so what I want to suggest is to introduce into the interface an explicit mention of this non-bottom decision value. Okay? And this will be an auxiliary, a Gauss variable, or a Gauss output, that will say, I gave you a value, but actually I also determined this non-bottom value. Okay? Now, just a side, like a small sidetrack about what auxiliary variables are, and they are typically their history or prophecy variables, and already mentioned today, so I will not really go deeply into them. They'll come back again. And usually what people use auxiliary variables for is to add them to the implementation or to an intermediate implementation level in order to prove correctness. What I think is quite lacking, and maybe these partial order things are somewhat of that nature that were mentioned by Grisha before me, but I haven't seen them used in the interface of the specification. Okay, so I want to add them to the specification and in particular to the interface. So what I'm going to have is I have an indicate as before. I have a response. The response have my response, what I get, but it also kind of says, in a way that I don't observe, it sets a Gauss variable, which is going to be the non-bottom response of the module. Okay? And again, I mark here that the implementation will still get the single response. Okay? But when the response happens, there will be a corresponding response with the Gauss variable that's, again, projected out. Okay. With this, actually specifying the crusader agreement becomes really simple. Okay. So first of all, we say that the Gauss variable is the same in all responses. Okay. Second, it should be the input of some correct process. And finally, if Vi is not bottom, it should be equal to the Gauss variable. Okay, so basically I get the feature that all non-bottom values are the same, okay, and are the input of some correct process.
So it's a prophecy variable in some sense here. Right?
Beautiful. Okay. Exactly. Beautiful. Prophecy variable in the specification.
In the specification.
Okay, good. So what I'm hiding here is that as long as we have just bottom responses, the Gauss variable, the Gauss output, is a non-deterministic choice. Okay, so whenever I have a bottom response, it could be that the Gauss variable is either 1 or 0. Okay, and I'm not really determining it, and it is indeed a prophecy variable. So here's an example what we can have. We can have, this is like, I get, the interesting cases are when the early responses have bottom value. Because once we have a non-bottom value, the Gauss output is determined. Okay? So I have a response, I just show the responses. Okay, so I have a response to I that is bottom, and I don't know what the output is. And then I have another response to J that I don't know what is bottom, and I don't know what the Gauss output is. And then somebody returns 1. And it could be, because of this non-determinism, and because it could be a prophecy variable, that in some other extension, J returns 0, and then, of course, the Gauss variable is also 0, and actually, then the next Gauss output must also be 0. Okay, so once the Gauss output is written, then it should stay the same. Okay, and in fact, so first of all, what we have here are just trace properties. Just I look at the single trace and I know whether it's correct or not. So in a sense, what we have is that we had a branch. This is the non-deterministic branch. But basically, when we branch to this, it's as if we retrospectively set this Gauss output to be 0, or when we branched here, we set this Gauss output to be 1. So that's really, it is a prophecy variable. Okay, so as I said, when we have a crusader agreement implementation, the underlying V might be determined by the future, how the execution develops, and it is therefore a prophecy variable. Now, with this in mind, you could see what could happen, or you could imagine, like get a glimpse of what's happening in these counterexamples to the randomized consensus. Because what happens is that the adversary goes here, injects here the common coin algorithm, okay, sees what the result is, and then goes back and fixes the history, what happened, fixes the past. Okay? So determines the prophecy variable in retrospect, in order to make it as bad as possible for our composition. Okay, and in order to deal with this, Abraham Ben David and Abraham et al., and in a different way in our paper, suggested the concept of binding crusader agreement. So what's binding crusader agreement? Basically, it says that the same non-bottom value is decided in all extensions after the first correct process returns. So you may not see, but actually the example has changed, and now in all extension, the Gauss variable is actually 1, and this should have been 1 as well, actually. Okay, so because the Gauss variable is 1, you can actually, something's wrong with my pictures, but basically once there's a single response, the Gauss variable gets set to the same value in all extensions. That's called, this is the binding property. And then, once we have this property, then the adversary cannot put its thumb on the scales and hurt the algorithm in the composition. Okay, so this is not a trace property. and it's actually a hyperproperty. Okay, because it's a property that talks about several extensions and several executions. Okay, so Giuliano, you know what will come on the next slide in a sense. So what should the Gauss variable be in order for the implementation to be binding? It was before prophecy variable. What it should be now?
History variable.
It should be a history variable. Okay. So we get there. We'll get there in a few minutes. Okay. I'll show you a slide that might have been good earlier. So it's one of my favorite. Okay. So I talked about an implementation, refining a specification. Okay. And the way these things are proved are through usually a combination of two simulations. One is called the forward simulation. Basically, we show that we give a mapping from states of the concrete, from the implementation, to states of the abstract implementation. And we show that whenever we have a transition from some concrete state to another concrete state, and if this concrete state is related to some abstract state, then there exists an abstract state that is related to the concrete state we transition to. Okay, so the simulation relation is shown to be mapped basically in a forward way. But sometimes, okay, so in forward simulations essentially rely on the history leading to the current state. Okay, so I get to CS1, and I know who I should map and make the transition to CS2, and I know which abstract state I need to map to. Okay. Sometimes it's not enough. ABD is actually a canonical example, by the way. And there you need to have a backward simulation. And a backward simulation, basically only based on what we have in the future, we decide what was the mapping for the earlier concrete state. Okay? And in a sense, backward simulations are basically capturing prophecies about the future and help us determine non-deterministic choices and the future that we don't know. And I really like two lovely papers that I think are underappreciated, work by Lynch and Van Drager and Johnson, both from the early 90s, that show that refinement can always be proved by a combination of forward and backward simulation. Interestingly enough, they prove the same result in different techniques. Okay, and I think they are worth studying. And if I had more time, I would bore you with some information about that. Okay. What I want to say, and already said, I think, is that binding crusader agreement, a crusader agreement implementation is binding if it is what we call a strong refinement of the specification. And this is the definition of what strong refinement is. This is from my work with Konstantin related to strong linearizability, which the main results were the Marquis result were about linearizability and strong linearizability, but actually were phrased for refinement in general. So I'm not expecting you to read this, but basically we've argued that a strong refinement is equivalent to having a forward simulation from the implementation to the specification. Okay, and which is equivalent to say that basically the Gauss variable is a history variable and there's no non-determinism in the way it's get bound. Okay, let's get set. Let me do another example, okay? Because I have 40 minutes. And also because there's a relation between the two problems, and because this will show you why good specifications are helpful because of functions. Okay, so there's an abstraction called gather. It's implicit in the famous Canetti-Rabin protocol that solves that shows asynchronous randomized consensus with an adaptive adversary for n larger than. Anyway, okay. So the clip here, the screenshot is from the paper by Abraham, Jovanovic, Mahler, whatever, et al. So like what 6 names? That's I woke up at before 2 a.m. Israel time, so anyway. Okay, so gather is an extension of reliable broadcast. So in the sense, the multiple processes broadcast their value, and everyone receives their value. So it's like, think of it as batched or like concurrent reliable broadcasts. Okay, and we have, I'll show you in a minute, the properties inherited from reliable broadcast. But we also have another feature, and this is of having a large common core. Okay, so I have my set, Giuliano has his set, Andre has its set, and it's guaranteed that there's a large, and there are various definitions how large is the large, but I'll pick a number. Okay, and there's a large core of processes whose values appear in the sets of all other processes. Okay? So going back to my whatever sermon, is I want to say, okay, let's call this common core. So actually, let me say one thing. The processes, the core exists, but the processes don't know what this core is. Because if they knew what the core was, they could solve agreement. Okay, so the magic of Canetti and Rabin is that the core exists, but the processes don't know what it is, because otherwise they couldn't solve it. Okay, so the core is not there explicitly. I get my set, you get your set, but we don't know what the common core is. I mean, if we could compare, of course, we would know what the intersection of us two is, but we don't know how we intersect with Andre, and Andre may actually show up in the future with his set. Okay, so again, Ghost outputs to the rescue. I say, I do an indicate of my input. I get a response which is a set. And somewhere, a Ghost output is also created with the common core. And now stating the properties is fairly easy. So there are these two simple properties. I'll go through them quickly, but they are the properties inherited from reliable broadcast. So if two correct processes have a pair for, I sometimes represent the sets as pairs, like index process ID value, and sometimes as vectors, just whatever is in my pictures. Okay? So if two processes, if Giuliano and I have a pair for Andre, it has the same value, whether Andre is good or not, as long as we are good. Okay? And if I'm correct, and Giuliano has a value for me, it is my input. Because these are properties inherited from reliable broadcast. We also have a property that the common core is included in my set. And we have a property that the common core is large. I use large to be n minus f, which in particular implies that the set I return is at least of size n minus f. Okay? And again, let's play with an example. So I'm paraphrasing now the common core property. There's a set of n minus f processes whose values appear in the set of every correct process. That's the way the common core is. And you can see here, in this example, this is for 4 processes and f equal 1. The first process returns actually as a full set, 4 values. And we don't know yet what the cost variable will be. And then another process returns the same set. And then another process returns no value 0, 1, 1. So we know here that the common core is basically, I'll mark it as 0, and no value 0, 1, 1. Okay? And let me go, I probably should have done this in 2 steps. Here, in this extension, the first process to return has 0, 0, 1, and no value for the last process. Okay? Which means that the common core will be 0, 0, 1, and no value. 0, 0, 1, no value. Okay? So you see I have 2 different common cores in these extensions. Okay? And you can build executions and algorithms that this is what you'll get. Okay? It's not like a figment of my imagination. There are algorithms, you can write standard algorithms, that's what you'll have. Some extensions you'll have this core, and in other extensions you'll have that core. And again, this is a trace property. You look at one execution, and you know what or you can say, or you can fix a common core. Now, by the way, if we kept getting, maybe not. Okay. Okay, so again, I do this trick that there's actually, if I look at the ghost variable, I'm mapped to two different executions. Okay, and you can define the binding common core in pretty much the same way. When the first correct process returns, there is a set that will be included in every response, regardless in all possible extensions. And actually, the example changed. Okay, and now the common core is bottom empty 0, 1, 1. Okay, and that's a hyperproperty as well. Okay, and we can basically do the same drill that we did with Crusader agreement. Okay, the implementation is binding if it is a strong refinement of the gather model, basically proved by simulation, and the ghost output is a history variable rather than a prophecy variable. Okay, so one reason to have good specifications is to be able to do reductions, is to use one module for solving another problem. Okay, and let me show you how binding gather, or let's say it this way, gather helps you solve Crusader agreement very easily. And if it's binding, then the Crusader agreement is also binding, which won't be surprising really once you see that. I mean, okay, so that's the algorithm. So I do a gather, I give my input, I do a gather, and then I look at the set that I returned. Okay, and if the set returns the size of my set minus f copies of the same value, I return this value. And otherwise, I return bottom. Okay, that's it. That's the algorithm. Okay, so here's, for example, one of my previous examples. Here, I don't have any majority. I mean, I have 0, 0, and 1, 1. So this return bottom. This will return bottom as well. This will return 1. This will return 0. And this will return actually 0 as well. Maybe I should return bottom here, but anyway, it doesn't matter. I mean, it doesn't make it wrong, but yeah. So, apologies again. Okay, so that's how the algorithm will operate. And let me show you the key lemma for its correctness. It's just because it's neat and it's simple. Okay, so the lemma on which the correctness rests is that if a non-bottom value v is returned by a correct process, v appears at least the size of the common core. I still don't know what the common core is, okay? But still, I know that the number of times v appears in the common core is the size of the common core minus f. So PI checked, a process checked based on SI, size of SI minus f, but I know that it will appear size of common core minus f times in the common core. Whatever it is, I don't know what it is, but it's still there. Now, obviously, if the lemma is correct, okay, by kind of intersection arguments, there can be, because the size of the common core is at least, I mean, be equal or larger than or equal, and n is larger than 3f, then at most one value can appear the size of the common core minus f times in the common core, and then if you return a non-bottom value, it's the same value. Okay, so if I have the lemma, I'm done. Now the proof for the lemma takes 4 lines. Okay. So let's look at the correct process. Actually, we can start saying the first correct process that returns, the first correct process that returns v. Okay? And v appears SI times, size of SI times minus f in SI. Okay, so let's look at this picture. This is SI. Somewhere in there, there's SC, the common core. And I'll call the rest of SI T. Okay? So the size of T is the size of SI minus the size of the common core, and it's at most F. Okay? Now let's look how the copies of V appear in the set SI. Okay? So let's assume, here's the picture. Let's assume V is the black. Okay? So let's assume all of T is black. Okay? So because this is biases away from the common core. So I actually don't really need to say that, but let's say for intuition. So how many times, okay, so the size of T is at most F. The number of times V appears in the core is the number of times it appears in SI. And in the worst case, all of T is V. Okay? So what is the size of T? The size of T is this value, is this quantity, size of SI minus the size of the core, the common core. And the number of times it appears in SI, V appears in SI, is size of SI minus F by our algorithm. So we cancel the size of SI and we get the lemma. Now, the lovely thing about that is that if gather was binding, then the value that appears size of common core minus F times in the common core is determined the first time the common core is determined. So V is determined once the common core is determined. Okay, so if SC is a history variable, if we have strong refinement, then the Crusader agreement is binding. And if not, so this just run through. This is the binding example of Crusader agreement. And if not, then it's not. Okay, so if the SC variable ghost output is a prophecy variable, then CA will not be binding necessarily. And we actually had an example before. So this concludes what as close as I have to real ideas. Next slide is even more speculative. It's a prophecy. So there's actually, I'm toying with properties like commitment that are used in cryptographic protocols. And so it's also a hyperproperty. So a commitment is I commit protocol and the value is revealed only after I start a reveal protocol and so on. And typical commitment, the committing process knows the value it is committing. Okay, so you could imagine how to specify it, although specifications are not that great either. But there's actually something called a random secret row, okay, in which the process who's doing the commitment doesn't know what it is committing. It's actually it's again implicitly used in Canetti and Rabin for the common coin, and a paper by Freitas et al. Has made it an explicit protocol. I don't remember, I took out the slide that shows the specification in their paper. It's like this long, lots of properties, etc. So you see a random secret row. I call the draw, I'm going to commit to a random coin. But when the protocol ends, I don't know which random coin I flipped. So it's committed, but I don't know. So it's secret from me as well, not just from everyone else. It's secret from me as well. You could imagine why you would want it, because then if I was Byzantine, I don't even know what I flipped, for example. So I commit to a random value V, and it's unknown to all processes, including PI itself. So you can imagine how I would state this. I do indicate draw, like I call the coin, and then I get a response that it's done, and it has a ghost output that is this randomly drawn number value from whatever domain I want it to be. And then also you need to ensure that it should be underscored, whatever, stays secret until it is revealed, but this is actually a kind of a non-interference property, which is kind of relatively well understood in the hyperproperty literature. So this is like my last slide. I'll wrap up. So binding is a hyperproperty that commits the outputs across all extensions from a particular point. Those outputs can expose and can capture such hidden commitments. And strong refinement, which is basically forward simulation based only on the history. So actually, to be honest, this is not totally correct. This doesn't hold for hyper-aliveness properties, and there are extensions of forward simulations that deal with this. But everything we deal with is mostly hyper-safety properties. So let me be imprecise here. And then strong refinement allows to enforce and state binding. And then composition easily preserves binding, as I've shown you in an example. And as I said, I'm trying to look at the commitment of probabilistic distributions and various other exciting stuff. So thank you.
Questions?
Like with binding, crusader agreement, binding gather, these are a bit difficult sometimes to achieve than the non-binding variants. Like they can be.
So actually you can achieve binding gather like with a little bit more work.
Yeah, a little bit more, but do you know of like a separation?
I wish. I wish. There is something that kind of claims that, but you need to go back and fix the... But I suspect there is a cost to binding, actually. I mean, actually the connection to strong refinement and the extra cost of strong refinement that we know in other contexts suggests that there is a way to prove that, but you know, Abraham et al. In another paper have something like that, but it's... And it's for crusader agreement and not for other.
Binding crusader agreement is sort of between crusader agreement and like adopt commit in terms of strengths, if you think about it. But you can turn adopt commit into binding crusader agreement.
Yes, I mean, again, depends which adopt commit version, extended adopt commit, etc. Yes, yes. Yeah. So the difference is like one time unit, so it's not like a huge difference. Yes. I mean, so I know when you write a protocol, and as I had this picture, like you run this more and more and more and more and more times, even a few like whatever will accumulate. So I'm not, but the difference is, which is actually harder to prove, you know, as a lower bound sometimes. Yeah. But that's an excellent question, actually.
So can you say slightly more about the previous example where you have this commitment to the probability distribution, I guess? What's the difficulty there?
Well, it's just, you know, you need to talk about, first of all, just talk about probability distributions and do it in this context, not in the, you know, I should have somewhere, let me see, I mean, I have some hidden slide. Yeah, let me show you this. I don't know what will happen if I show the slide. Okay, so that's, you know, that's the way it's specified, and that's, I think, not all of it. Okay, it's like I had this slide, and it's like, what? Okay, so just translate. I mean, I think there's even more stuff that's lacking, but I feel that one of the problems is that just a lack of sufficient language to talk about properties. And, you know, cryptographers like this ideal functionality. I think it's my sense as somebody who's kind of probably a very Frida person, like in between algorithms and formal verification and etc., is that it's not the sort of thing that works well. It's just, and I can say more about that, but reception and such. Yeah. I don't want you to hate me, and everybody will finish the food in the reception.
More questions?
I will take another question if necessary, if somebody has.
Okay, well, let's thank Hegit again.